In today's lesson, we're going to look at linear inequalities in two variables. Steve's going to look at linear inequalities in standard form, and Anne's going to look at applications. I'm going to look at linear inequalities of the form x is greater than c, linear inequalities of the form y is greater than c, and linear inequalities of the form y is greater than mx plus b. Notice this is slope-intercept form. In all of these, we can replace the greater than symbol with a less than symbol, a greater than or equal to symbol, or a less than or equal to symbol. We'll look at different combinations. I'm going to end with a brief summary of some of the things we learned about linear inequalities in two variables. So let's start by looking at linear inequalities of the form x is greater than c. I want to start by looking at a linear inequality in just one variable. Let's recall what it means to plot the solution to x is less than or equal to 5 on a number line. So we would need a point at x equals 5, and then we would shade everything to the left of x is equal to 5. This gives all the values where x is less than 5. So let's extend this into linear inequalities in two variables. What if we want to plot the solutions to x is less than or equal to 5 in the coordinate plane? Well, we can start with the x-axis. That's just a number line. So we'd plot our point at x equals 5 and then shade to the left of that. Well, in the coordinate plane, there are lots of points where x is equal to 5. For instance, the point 5, 4 has an x value of 5, and anything to the left of this point would have x values less than 5. The point 5, negative 3 also has an x value of 5. Anything to the left of this point would have x values less than 5. The point 5, negative 6 has an x value of 5, and anything less than this would have x values less than 5. In fact, we've talked about what all of the points in the coordinate plane where x is equal to 5 looks like. It's just a vertical line. So if we start with a vertical line through the point 5, 0 on the x-axis, we've got all of the points in the coordinate plane where x is equal to 5. And as we've seen, shading to the left of this gives us points where x is less than 5. So let's just shade everything to the left of the vertical line. This gives us all of our solutions to x is less than or equal to 5, an infinite number of points or ordered pairs. So let's think about three particular solutions to x is less than or equal to 5. Any point on the line gives us an x value of 5. So for instance, the point 5, 5 has an x value of 5. This satisfies the inequality. I can also pick any point to the left of the line. For instance, the point negative 1, 2 has an x value less than 5. Or I could pick a point that I don't even see on the screen. I could say that a point like negative 100, 70 would also satisfy this inequality. X is less than 5 if x is negative 100. So there are an infinite number of ordered pairs that satisfy this inequality. Three particular solutions are the ones that we've discussed here. So three solutions to x is less than or equal to 5 are 5, 5, our point on the line, negative 1, 2, and negative 100, 70. These last 2 points lie to the left of the vertical line, x equals 5. Now let's plot the solutions to x is greater than negative 3 in the coordinate plane. Well, we can start by thinking about what we call a boundary line. X equals negative 3 is going to be our boundary line. X equals negative 3 is a vertical line through negative 3, 0. In this case, our boundary line is not included because we're only looking for x values strictly greater than negative 3. So when we sketch our boundary line, the way that we indicate it's not included is to use a dashed line. So we have a vertical dashed line through the point negative 3, 0. Now we want x values that are greater than negative 3. As we move to the right of this line, all of the x values will be greater than negative 3. So we need to shade to the right of this line. Well, let's think about three particular solutions to this inequality. Since we have a dashed line, points on the line are not included. So when I think about three solutions, I want to make sure I don't pick a point on the line. I can pick a point very close to the line, though. For instance, I could take the point negative 2.9992. This would satisfy the inequality. X having a value of negative 2.999 is greater than negative 3. And I can pick any other point in my shaded region. For instance, the point 4, 6 satisfies this inequality. Since x is 4, 4 is greater than negative 3. This satisfies the inequality. And I could pick a point like negative 1, negative 4. The x value is negative 1, and negative 1 is greater than negative 3. So 3 solutions to x is greater than negative 3 are negative 2.9992, 4, 6, and negative 1, negative 4. Again, there are an infinite number of solutions. We've just named 3 of them. So now let's look at linear inequalities of the form y is greater than c. Let's say we want to plot the solutions to y is less than 4 in the coordinate plane. Well, we can start by thinking about our boundary line. In this case, our boundary line will be y is equal to 4. And we know what lines like y is equal to 4 look like. When we have y is equal to a constant, we have a horizontal line. In this case, we have a horizontal line through the point 0, 4. This time we have a strict inequality. Y is strictly less than 4. So the boundary line is not included. We need a dashed horizontal line through 0, 4. Now we're looking for y values that are less than 4. Y gets smaller as we move downwards, so we need to shade below this line. Anywhere below this line, our ordered pairs are going to have a y-coordinate less than 4. Let's look at 3 particular solutions to y is less than 4. The line itself is not included, so I want to make sure that I don't pick a point on the line, but instead only choose points that lie below the line. So for instance, the point negative 5, 2 satisfies this inequality. The y value is 2, and 2 is less than 4. The point 4, 1 also satisfies this inequality. And the point 1, negative 2 satisfies this inequality. So 3 solutions to y is less than 4 are negative 5, 2, 4, 1, and 1, negative 2. Now let's plot the solutions to y is greater than or equal to negative 6 in the coordinate plane. This time our boundary line is y is equal to negative 6. Again, we're looking at a horizontal line. This time, a horizontal line through 0, negative 6. And this time our boundary line is included because we're looking for y values greater than or equal to negative 6. Any point on the horizontal line y is equal to negative 6 has a y-coordinate of negative 6. Since we're looking for y values greater than negative 6, we're looking for y values above this line. As we move above the line, the y-coordinates are always larger than negative 6, so we shade above the line. Let's look at 3 particular solutions to y is greater than or equal to negative 6. This time the line is included, so I could pick a solution on the line. I could pick all 3 of my solutions on the line if I wanted to. I'm just going to pick one solution on the line, negative 3, negative 6. And then I'm going to pick a couple of points above the line. 2, 1, for instance, is a solution to y is greater than or equal to negative 6, because the y-coordinate 1 is greater than negative 6. Negative 3, 2 also satisfies this inequality. So 3 solutions to y is greater than or equal to negative 6 are 2, 1, negative 3, 2, and negative 3, negative 6. Now I want to look at linear inequalities in slope-intercept form. Let's start by plotting the solutions to y is less than or equal to x in the coordinate plane. This time my boundary line is y is equal to x. If I think of this as being in slope-intercept form, then the slope of the line is 1, b is 0, so that tells me that the vertical intercept is the origin, 0, 0. So if I start with the vertical intercept and use a slope of 1, which I can think of as the fraction 1 over 1, so a rise of 1 and a run of 1, a rise of 1 and a run of 1, then I get an idea of where the line is. This time the boundary line is included because we're looking at y is less than or equal to x. So I need to draw a solid line through y is equal to x. Now I need to decide, do I shade above this line or do I shade below this line? Well, if I think about a point on the line, for instance the point 3, 3, in this case y is equal to x. In fact, any point on the line is going to have a y value that's equal to x. The other part of this inequality is y is less than x. So let's think about points above and below the line. If I choose a point above the line, such as the point 3, 5, then y is greater than x. We're looking for y is less than x. If, however, I pick a point below the line, such as the point 3, 1, then y is less than x, and that's what we want. So we need to shade below the line. We can think of the shading here as being half of a plane. So the half plane that we've shaded is below the line. This time the line is also included in our solution. Let's name 3 solutions to y is less than or equal to x. So I can pick any point on the line. That's going to be where y is equal to x. For instance, the point negative 3. Negative 3 satisfies the inequality because y is equal to x. The point 2, 0 also satisfies the inequality. Here, y is less than x. The point 6, 4 also satisfies this inequality. So 3 solutions to y is less than or equal to x are negative 3, 2, 0, and 6, 4. Now let's plot the solutions to y is strictly greater than x in the coordinate plane. This time again our boundary line is the line y is equal to x. But we're going to draw a dashed line because the boundary line is not included. We only want values of y that are strictly greater than x. So we draw our line y equals x with a dashed line, and we want to pick y values that are greater than x. Well, we discussed if we pick a point on the line, y is equal to x. We don't want y is equal to x, so we drew a dashed line. If we pick points above the line, y is going to be greater than x, so I need to shade above the line. Let's think about 3 particular solutions to y is greater than x. The line's not included, so I want to make sure I don't pick any points on the line, but instead pick points above the line. For instance, the point negative 2, 2. Since y is 2 and x is negative 2, y is indeed greater than x. Another point that satisfies this inequality is 2, 3. And a third point that satisfies this inequality is negative 5, negative 2. So 3 solutions to y is greater than x are 2, 3, negative 2, 2, and negative 5, negative 2. Of course, there are an infinite number of solutions to this inequality. These are just 3 of them. Now let's plot the solutions to y is greater than 2x minus 3 in the coordinate plane. This time my boundary line is y is equal to 2x minus 3. This line has a slope of 2 and a y-intercept of 0, negative 3. So starting at my y-intercept of 0, negative 3, a slope of 2 I can think of as the fraction 2 over 1, a rise of 2 and a run of 1, rise of 2, run of 1, up 2 over 1. When I sketch the line, I need to think about the inequality. I have strictly greater than as the symbol in my inequality, so I know that the line is not included. We indicate that with a dashed line. So when I sketch the line, I want to make sure that I sketch a dashed line. And I need to think about, do I shade above this line or do I shade below this line? Well, if I pick a point on the line, we discussed that points on the line are points where y is, in this case, equal to 2x minus 3. So, for instance, the y-intercept 0, negative 3 is a point where y is equal to 2x minus 3. If I substitute 0 for x, 2 times 0 minus 3 is negative 3, and y is negative 3. If I pick a point above the line, then the y-coordinates are greater, so y should be greater than 2x minus 3. Well, let's actually test with this point 0, 1, which lies above the line. So here we have an x-coordinate of 0 and a y-coordinate of 1. So if x is 0 and y is 1, we need to ask ourselves, true or false? Is y greater than 2x minus 3? Well, let's substitute 1 in place of y, and we want to know, is 1 greater than 2 times 0 in place of x minus 3? Well, 2 times 0 minus 3 is 0 minus 3, which is negative 3. So we end up with 1 is greater than negative 3. This is true. So indeed, on points above the line, y is going to be greater than 2x minus 3. So I want to shade above the line. Now, as you're shading these inequalities by hand, there's lots of different ways that you can shade. You can just use a pen or pencil and roughly shade it, like I'm doing here. You might use a highlighter so that you can shade it more thoroughly. I've even seen students using crayons as a quick way to shade inequalities. You decide what's going to work best for you. Now let's plot the solutions to y is less than or equal to 15x minus 5 in the coordinate plane. So if I think about my boundary line, again, it's in slope-intercept form. My boundary line is y is equal to 15x minus 5. So in this case, my y-intercept is 0, negative 5. The slope is 15. So if I start at the y-intercept 0, negative 5 and think of a slope of 15, in fractional form we could think of 15 over 1. So if I rise 15, I need to run 1. But if I start at 0, negative 5 and try to rise 15, I'm going to be off this grid. So I think I want to start with a blank sheet of graph paper and set up my own axes. So in this case, I need to make sure that on the y-axis I'm able to plot the point 0, negative 5. And also that I'm able to use the slope of 15. As I'm thinking about my scales for my axes, I need to make sure I can plot the point 0, negative 5 and use my rise of 15. So I think on the y-axis, it would make sense to use a scale of 5. That should work here. What about the scale on my x-axis? Well, if I rise 15, I need to run 1. So I think I'm just going to use a scale of 1 on the x-axis. So starting at my y-intercept, 0, negative 5, a rise of 15 corresponds to a run of 1. So up 15 over 1. Since y is less than or equal to 15x minus 5, the boundary line is included in the solution set. So I want to make sure that I draw a solid line through these points. And then I need to decide, do I shade above or below the line? Well, my instincts tell me to shade below the line because I'm looking for not only points where y is equal to 15x minus 5, which occurs on the line, but where y is less than 15x minus 5. And y gets smaller as we move downwards. So let's test a point below the line. How about the point 3, 5? So what I need to ask myself is a true or false question. If x equals 3 and y equals 5, true or false? Is y less than or equal to 15x minus 5? Well, let's substitute 5 for y and 3 for x. So is 5 less than or equal to 15 times 3 minus 5? 15 times 3 is 45. 45 minus 5 is 40. 5 is definitely less than 40, so this is true. So as my instinct told me, I need to shade below the line. 3, 5 is a solution to this inequality. So I'm going to shade everything below the line. So now I want to summarize some of the things that we've talked about in this portion of the lesson. We're looking at linear inequalities in two variables. A line divides the coordinate plane into two half-planes. When graphing a linear inequality, we need to decide which half-plane to shade, the half-plane above the line or the half-plane below the line. For instance, in y is greater than or equal to x, we shade the half-plane above the line. When y is less than or equal to x, we shade the half-plane below the line. Inequalities involving less than or equal to or greater than or equal to include points on the line in their solution sets, so we use solid lines, such as in y is less than or equal to x. Inequalities involving strictly less than or strictly greater than do not include points on the line in their solution sets, so we use dashed lines, as in y is less than x. So now I want to turn this over to Steve, who's going to look at linear inequalities in two variables, but his inequalities are going to be given in standard form.
Hello. As Candace promised, I'm going to follow up talking more about linear inequalities in two variables. Candace ended her part of the lesson talking about linear inequalities in slope-intercept form. I'm going to briefly review that, and then I'm going to talk about manipulating inequalities given in standard form so that they are inequalities in slope-intercept form. I'm going to follow that by showing you a totally new method for graphing inequalities after testing a point. And I'm going to finish up by turning the picture around a little bit, and we're going to write an inequality from a given graph. So let's talk about manipulating inequalities given in standard form. But before we get to a specific example, let's review what Candace was just talking about. The solution set to the inequality y is less than or equal to mx plus b is the set of all points on or below the line y equals mx plus b. The solution set to the inequality y is greater than or equal to mx plus b is the set of all points on or above the line y equals mx plus b. In either case, the line y equals mx plus b is called the boundary or boundary line of the solution set. In these two cases, points on the boundary line are included as solutions to the inequality. The solution set to the inequality y is less than mx plus b is the set of all points below the line y equals mx plus b. The solution set to the inequality y is greater than mx plus b is the set of all points above the line y equals mx plus b. In both of these cases, the line y equals mx plus b is still called the boundary or boundary line of the solution set. The difference here is that points on the line are not included as solutions to the inequality. So let's graph the solution set to the inequality 2x plus 5y is less than 7. This inequality has been given to us in standard form. If we want to use the tips posted on the last two screens, the first thing we need to do is manipulate this inequality into an equivalent inequality that is in slope-intercept form. I want to isolate y by itself on the left side of the inequality symbol. So let's start with our given inequality. 2x plus 5y is less than 7. And the first thing I want to do is subtract 2x from both sides of the inequality. That's going to give me 5y is less than 7 minus 2x. Now, to completely isolate y, I need to divide both sides of the inequality by 5. So we have 5y over 5 on the left, and we have 7 minus 2x over 5 on the right. Now, you might be thinking, where's the inequality symbol? I'm reminding you that whenever you multiply or divide an inequality, you need to think about the sense of the inequality. When you multiply or divide by a positive number, the sense remains the same. When you multiply or divide by a negative number, the sense reverses. In this case, we're dividing by positive 5, so our less than sign remains a less than sign. So we're left with y is less than, breaking this up into two fractions, 7/5 minus 2/5 x. Here is our equivalent inequality in slope-intercept form. So the first thing we need to do is consider our boundary equation. We need to graph the line y equals negative 2/5 x plus 7/5. I'm going to be doing quite a bit of work in my head today. The reason I'm going to do that is because I want to encourage you to try and do some of this line plotting, doing the calculations in your head. If it works, that's great. If it doesn't work for you, if you have more success using some scratch paper or creating a table by hand, that's great too. I'm just encouraging you to experiment. Do what works for you. So the first thing I need to do is I need to find a point on the line. Now, I could use the vertical intercept. That is the point that I get when x is 0. But when I replace x with 0, y comes out to be negative 2/5 times 0, which is 0, plus 7/5. So the vertical intercept is the point 0, 7/5. I don't think I'm going to use that as my anchoring point because I cannot plot the point 0, 7/5 exactly. The scale on both my axes are integer scales. So I think a better anchor point for my line would be a point where both coordinates are integers. So I'm going to keep thinking about different values of x until I stumble upon a value of y that is an integer. So what is the value of y when x is 1? Well, when x is 1, y is negative 2/5 times 1, which is negative 2/5 plus 7/5. That gives me negative 2 plus 7, which is 5 over 5. Hey, 5 over 5, that's 1. 1's an integer. We're good to go. When x is 1, y is 1. The point 1, 1 is on the line. So let's go ahead and plot that point. Now we can see by our coefficient on x that the slope of the line is negative 2/5. I can think of negative 2/5 as positive 2 over negative 5. That would mean that I would have a rise of positive 2 for a run of negative 5. I also could think of negative 2/5 as negative 2 over positive 5. That would mean I would have a rise of negative 2 for a run of positive 5. I've got several points on my line, so let's get out the ruler and connect the dots. Now, before I actually lay the pen onto the screen, I need to look at my inequality because I need to decide, do I want to draw this line solid or do I want to draw it in a dotted or dashed fashion? Since points on the boundary are not solutions to this particular inequality, it's strictly less than inequality, I want to draw the line in a dotted or dashed fashion. Now, I anticipated I may not draw the best line in the world here, so on the next screen, I went ahead and had the computer draw the line for me so that we have a really good boundary for sketching our solution set. So our original inequality is equivalent to the inequality y is less than negative 2/5 x plus 7/5. When y is less than the expression involving x, the solution set is the half plane below the line. So our solution set is all of the points that lie below the line. Now, even though I'm pretty confident about this solution set, I am going to mentally check a point to make sure that I did shade the proper side of the line. I'm going to try and find a point that's going to require the simplest arithmetic possible. And we're pretty lucky that the origin is part of what seems to be the solution set, and it's pretty easy to check arithmetic when x is 0 and y is 0. When y is 0, the left side of the inequality is 0. When x is 0, the right side of the inequality is 7/5. Is it true that 0 is less than 7/5? You betcha. So we have the proper side of the line shaded. Let's see another example. Let's graph the solution set to the inequality 7 is greater than 5x minus 3y. I want to isolate y, and I want to isolate y on the left side of the inequality. So we have 7 is greater than 5x minus 3y. The first thing I want to do is move the y term to the left. I can do that by adding 3y to both sides of the inequality. That gives me 3y plus 7 is greater than 5x. Now I want to move the 7 to the right side of the inequality. I can do that by subtracting 7 from both sides of the inequality. That gives me 3y is greater than 5x minus 7. Now I need to divide both sides of the inequality by 3. So we have 3y over 3 on the left, 5x minus 7 over 3 on the right. Since I divided both sides by a positive number, the sense of the inequality remains unchanged. The greater than sign is still a greater than sign, and so I'm left with y is greater than 5/3 x minus 7/3. When graphing the solution set, the first issue is, where does the boundary line lie? Well, thinking about things I discussed in the last example, the first thing I want to do is come up with a point where both coordinates are integers. Now, thinking about this, since both fractions on the right side of the equal sign have a denominator of 3, I could write the right side of the equal sign as 5x minus 7 over 3. So if I'm going to test certain values of x to see whether y comes out to be an integer, what I need to do is determine whether the expression 5x minus 7 is or is not evenly divisible by 3. For example, when x is 0, the expression 5x minus 7 simplifies to negative 7. Negative 7 is not evenly divisible by 3, so I will not get an integer value for y. When x is 1, the value of 5x minus 7 is negative 2. Again, I will not end up with an integer value for y. When x is 2, the value of 5x minus 7 is positive 3. Bingo! 3 is evenly divisible by 3. 3 goes into 3 one time. When x is 2, the value of y is 3 over 3, which is 1. I'm going to use the point 2, 1 as my anchor point. So in our boundary equation, we determined that the point 2, 1 lies on the line. And if we look at the equation, we see the coefficient on x is 5/3, so the slope is 5/3. So let's go to the point 2, 1, and let's plot a couple points using a slope of 5/3. A rise of 5, a run of positive 3. A rise of negative 5, a run of negative 3. There's our 3 points. Looking at my inequality, it's a strictly greater than sign, which means points on the boundary are not included in the solution set. So I draw my boundary in a dotted or dashed fashion. So now we need to decide which half plane to shade. Do we want to shade above the line or below the line? Y is greater than 5/3 x minus 7/3. We need to shade above the line. Lucky for us, once again, 0, 0 is in our proposed solution set, and I can mentally check. When y is 0, y is 0. When x is 0, 5/3 x minus 7/3 is negative 7/3. 0 is greater than negative 7/3. We did shade the proper side of the line. Let's talk about a different method for figuring out which side of the line to shade. This is called graphing inequalities after testing a point. I want to solve the inequality 2x minus 5y is less than 10. I could manipulate this into slope-intercept form, but I think I can come up with a plan that I actually could graph the solution set a little more quickly. I am looking at this boundary equation, 2x minus 5y equals 10, and I'm thinking to myself, you know what? I can find the x and y intercepts really easily in my head. The x-intercept is the point where y is 0. In my boundary equation, if I replace y with 0, I'm just left with 2x equals 10. I can solve that in my head. X is 5. So the x-intercept is the point 5, 0. The y-intercept is the point where x equals 0. In my boundary equation, if I replace x with 0, I end up with negative 5y equals 10. I can solve that in my head. Y is negative 2. So in my head, I have figured out what the two intercepts are. Let me remind you that if you need to use some scratch paper to figure that out, that's great. I'm just encouraging you to experiment to see if you can successfully do this in your head. Alrighty, we've got our two intercepts, the point 5, 0, and the point 0, negative 2. I can see from these 2 points, moving from the right point to the left point, that the slope of this line is going to be negative 2 over negative 5. That is a slope of 2/5. Let's do negative 2 over negative 5 to get a third point to help us line up our ruler. When I connect these dots, I need to notice that the inequality is strictly less than, so my boundary needs to be dashed or dotted. Alrighty, so now the issue is, which side of the line do we need to shade? I know what some of you are thinking. Some of you are thinking there's a less than sign, so we need to shade below the line. Well, the problem with that is that a less than sign indicating shading below the line is only 100% valid when your inequality is given in slope-intercept form or written in slope-intercept form. This inequality is not in slope-intercept form, so I do not know that I need to shade below the line. As a matter of fact, let's check that out. Let's test a point below the line in our inequality. So let's look at the point 0, negative 4. Does that satisfy our inequality? If x equals 0 and y equals negative 4 is 2 times x minus 5 times y less than 10. Well, let's check it out. 2 times 0 minus 5 times negative 4. Is that less than 10? 2 times 0 is 0. Negative 5 times negative 4 is 20. 20 less than 10. That would be the big false. Since a point below this line does not satisfy the inequality, it must be the case that the half plane below the line is not the solution set. The solution set must indeed be the half plane above the line. So that's what I'm going to shade. So let's summarize this new strategy. Begin by graphing the linear equation that results from replacing the inequality symbol with an equal sign. Graph the line using a connected line if the inequality symbol is greater than or equal or less than or equal. Graph the line using a dotted line if the inequality symbol is greater than or less than. Test any point that doesn't lie on the line in the original inequality. If the tested point makes the inequality statement true, shade that side of the line. If the tested point makes the inequality statement false, shade the other side of the line. Before I leave this screen, I do want to mention a mistake that I've seen people make on this step. test any point that doesn't lie on the line in the original inequality? There's a couple mistakes I've seen people make. One mistake I've seen them make is they'll test a point that's not on the line in the boundary equation. Well, that's inevitably going to be false because the only solutions to the boundary equation are points on the line. Another mistake I've seen people make is they'll test a point on the line. Well, if you test a point on the line, that's really not going to give you any indication whether you need to be above or below the line. So watch out for those two common errors. Let's graph the solution to the inequality 3x plus 5y is less than or equal to negative 15. Now remember, one of the things I'm doing in this lesson is to encourage you to try doing some of the steps in the graphing process in your head. My boundary equation here is 3x plus 5y equals negative 15. I can figure out both of the intercepts in my head. When x is 0, we're left with the equation 5y equals negative 15. The solution to that equation is negative 3. So the x-intercept is the point 0, negative 3. When y is 0, we're left with the equation 3x equals negative 15. The solution to that equation is negative 5. So the point negative 5, 0 is the x-intercept. Let's plot our points. We've got the point 0, negative 3. We have the point negative 5, 0. I can see, looking left to right between these 2 points, if we have a rise of negative 3 and a run of 5, we get to another point on the line. So let's do another rise of negative 3 and run of 5. I've got 3 points. That'll allow me to line up my ruler pretty well. This time, when I look at the original problem, the inequality symbol is less than or equal. Since we have the or equal part, and points on the line is where the two sides of the inequality are equal, I am going to connect these points with a solid line. So now the issue is, do I shade the half plane above the line, or do I shade the half plane below the line? Well, all I need to do is test any point not on the line in the inequality. For example, the point 0, 0. It's not on the line. So let's use that as our test point. Now I'm going to both do this in my head and write it out just because I want to make sure you have the method down, but also because I want to encourage you to do some of the thinking in your head. When x is 0 and y is 0, the left side of the inequality is 0 plus 0, which is 0. So we're left with the inequality 0 is less than or equal to negative 15. That is not a true statement. 0, 0 is above the line. A point above the line makes the inequality false. So the half plane above the line, that's not the solution set. It's the half plane below the line that is the solution set. So let's recall how I made that determination. If x equals 0 and y equals 0, the question is 3x plus 5y less than or equal to negative 15? 3 times 0 plus 5 times 0. Is that less than or equal to negative 15? Is 0 less than or equal to negative 15? That is not true. That's false. No, 0 is not less than or equal to negative 15. 0, 0 is above the line, so the solution set is not the half plane above the line. It's the half plane below the line. Now let's look at the inequality 3x minus 4y is greater than or equal to negative 2. Now quickly in my head, when I think about intercepts, when I replace x with 0, y comes out to be, if I was looking at the equation, negative 2 over negative 4, which isn't an integer. And if I replace y with 0, x comes out to be negative 2 over 3, which isn't an integer. Since neither my x-intercept nor my y-intercept has 2 coordinates, both of which are integers, I will not get a very accurate graph if I plot these 2 points and try connecting the lines. So I have a decision to make. I need to consider my options. I need to choose a method that works for me and works for the problem. Now, one thing that I could do is I could bumble about in my head and try and come up with 2 points that are on the line 3x minus 4y equals -2, that both coordinates are integers. But I think I'm going to choose a different strategy. I think I'm going to go back to the slope-intercept model. So the first thing I need to do is isolate y by itself. So I've got 3x minus 4y is greater than or equal to -2. Subtracting 3x from both sides of the equation, I have -4y is greater than or equal to -2 minus 3x. Now I need to divide both sides of the inequality by -4. So the left side's going to be -4y over -4, and the right side's going to be -2 minus 3x over -4. Boy, it's a good thing I've gotten into the habit of not writing down my inequality sign when I perform a multiplication or division step, because this time I am dividing both sides of the inequality by a negative number. You know what that means? It means the sense of the inequality changes. My greater than or equal to sign needs to become a less than or equal to sign. So I'm left with y is less than or equal to -2 over -4 minus 3x over -4. So this simplifies to y is less than or equal to +1/2 minus a negative gives us plus 3/4 x. So our boundary equation is y equals 3/4 x plus 1/2. I can use my slope 3/4 to find my second point and my third point, but I need to come up with some point on this line as my anchor point before I can start using that slope. So let's think about values of x. What is y when x is 0? Y is 1/2. I don't want to plot the point 0, 1/2. What is y when x is 1? Y is 3/4 plus 1/2. Even if I don't know what 3/4 plus 1/2 is, I do know it's not an integer, so I don't want to plot that point. What is y when x is 2? Well, let's see. 2 over 4 is the same as 1 over 2. So when I replace x with 2, I'm going to have 3 over 2 plus 1 over 2. That's 4 over 2. 4 over 2 is 2. That's an integer. So the point 2, 2 is on the line. Both coordinates are integers. That's a good anchor point. So let's go ahead and plot our anchor point 2, 2. And then let's use our slope of 3/4 to get a couple more points on this line. We can think of 3/4 as a rise of 3 and a run of 4. We can also think of 3/4 as -3 over -4. That would be a rise of -3 for a run of -4. A rise of -3 for a run of -4. Before I actually draw the line, I need to look at my inequality symbol again. Since this is less than or equal to, and points on the line are where the two expressions are equal, I need to draw a solid line. Now my original inequality has been manipulated into slope-intercept form. The equivalent inequality is y is greater than or equal to 3/4 x plus 1/2. Points on the line, they're part of the solution set. That's why we have a solid line. The other points that are in the solution set are points that are above the line. Let's make sure that our solution set makes sense. I think I'm going to pick the point 0, 4 because the origin's kind of an iffy point in this particular picture. So if I look at the point 0, 4, what do I get in my inequality? Well, the left side of the inequality is y, which is 4. The right side of the inequality is 3/4 x plus 1/2. That's 3/4 times 0, 0 plus 1/2. Is 4 greater than 1/2? You betcha. So we shaded the proper side of the line. Before I leave this example, let me remind you that I made a choice at the beginning of this problem to approach the problem from a slope-intercept perspective. That was not the correct choice. That was just the choice I chose to make. If you find that you're more successful trying different values of x until you get 2 points, both of which have 2 coordinates that are integers, and then using the testing a point model, that's great. Do what works for you. Let's do one last example where we are given the graph and come up with the inequality that produced the graph. So let's find an inequality that describes the given solution set. Well, the first issue is, what is the equation of our boundary line? Well, looking at this line, I can see that the vertical intercept, the y-intercept, is the point 0, 2. And looking at another point on the line, say the point -3, +3, I can see that the slope of this line is -1 over +3. So using the slope-intercept form for the equation of the line, I know that the boundary equation is just y equals -1/3 x plus 2. What inequality describes points above the line? Well, we know that our boundary equation is y equals -1/3 x plus 2. We know that points on the line are not included in the solution set because the line is dashed. So we need to either put a greater than symbol or a less than symbol between our two expressions. Well, since we have our boundary equation in slope-intercept form, and we know that we're looking for points above the line, we know that y needs to be greater than -1/3 x plus 2. Before I leave this example, I'm going to check a point, just to double check my work. Let's check the point 0, 3. If I replace y with 3, the left side of the inequality is 3. If I replace x with 0, the right side of the inequality is 2. 3 is indeed greater than 2. So we seem to have had success. That's it for me. Now Anne's going to come work some application problems for you.